So basically, I'm affiliated to something in Paris. So of course, Paris being the center of the world in France. But I'm living in Nice, close to Nice, in Sophie Antipolis, because there is an antenna of something from Paris in Nice. So at the end, I have 3 institutes, CNRS, INRIA, and MIN Paris. That's the complexity of the French system.
Yeah, okay. Looking forward to this talk on turbophoresis of heavy particles.
Okay, so I'm going to talk again about particles and again about turbulent flows, and with the same applications in mind. So I was a bit scooped by Herman, so I will not talk about these things. I will maybe just talk a bit about planet formation, because it's another problem, natural problem, where one needs to understand interactions between particles and how they are distributed in the flow. So it's basically very different from geophysical settings, because it's particles in rotation with a very strong shear. So because of Keplerian rotation along the star, so it's making things very different. And for instance, it's making, for instance, heavy particles to concentrate inside vortices instead of being ejected, as we have seen, because of Coriolis forces. So the question is that I want to address is, how can we try to predict or quantify the concentrations of such heavy particles for ranges which are inside the inertial range of the turbulent flow? So basically, I will simplify a lot the particle equation. So I'm considering that the outer flow is maintained in some kind of statistical steady state, so homogeneous isotropic flow, and incompressible, of course. And then I will consider particles which are everything but light. So they will be heavy, very small, rigid, dilute. So with no slip, I mean almost no slip with the flow, because they will have a very small Reynolds number. And then so that I can simplify everything in the Maxey-Rayleigh equation and just write that they are filling the Stokes drag with the flow. So I'm not even considering gravity there. And so everything here is described in terms of one parameter, which is the response time of the particles, which relates to the size and the density ratio and the kinematic viscosity of the fluid. So now in my problem with the flow and the particles, I have a number of dimensionless parameters. So the Reynolds number of the flow, which is measuring the fluid inertia, which I suppose very large, and which is giving the ratio between the large scale and the small scale of my flow. Then I have particle inertia, which is the ratio between the response time of the particle and a typical time of the flow that I will choose to be the smallest time scale I have in my flow, which is the Kolmogorov time scale, the dissipative time scale. And then I will assume to be in the very dilute limit that my volume fraction is very low, so that I can neglect all the interactions between the particles. I'm simplifying a lot. So now, what is known about particle clustering is that usually people are considering two phases of this clustering. So what's happening at very small scales, so below the dissipative scales, inside the dissipative scales of the flow, where typically, because of their dissipative dynamics, particles are concentrating on some kind of fractal or multifractal sets. And then what you observe when you look at the particle distribution in physical space is some kind of projection of this fractal set, which is giving some non-trivial dependence on scale on the particle distribution. And then what is known from larger scale, so inside the inertial range, is that there are very strong fluctuations in the particle distribution. So some voids, some clusters, which are having scales which are spanning the whole inertial range. And this, even if the Stokes number is small, even if the particles are just feeling what's happening at dissipative scale, what you observe is that you have this kind of inhomogeneities. So I think that this is something, so it's a cut of a 3D particle distribution, and for Stokes number of the order of unity. Yeah. And what is believed to explain this kind of fluctuations is the mechanism of ejection from eddies, so the centrifugal mechanism, where particles are tending to get concentrated in regions in between the eddies. This is what is believed, and the question I want to address is how to model and quantify. So there have been some measurements. For instance, a typical measurement is what is called the radial distribution function, so which is telling you what is the excess of particles you observe compared to a uniform distribution, looking at pairs of particles. So you sit on the particle and you look at how many particles you have at a distance L from this particle. And so this excess here is shown as a function of the scale. So for Stokes numbers of the order of unity. And so what is well known and used in models for collisions, etc., is that you have this power law divergence at very small scales, which is the preferential concentration usually used. And then typically you have a different law at inertial scales, which seems to depend not that much on the Reynolds number, except at the very large cutoff. And the only prediction that you have for the way things are depending here on the scale is an old paper, which is more than 20 years old, by Balkowski and Falkovich and Fuchson, which is telling you that it should be some kind of activation process, like exponential of minus a negative power of the scale. Okay, so that's the state. And as you see, so maybe asymptotically you will look like that, so in the limit of infinite Reynolds number, but I mean, it's not that much convincing anyway. So then there is another thing that has been studied, is the distribution of voids in the particle distribution. So this started in 2 dimensions, basically by, again, something which is almost 20 years old, by Guido Boffetta and collaborators, where they were able to rescale in 2 dimensions the distribution of void and show that it was becoming independent of the Stokes number. And more or less at the same time, Goto and Vassilikos, they got some hand-waving ideas on how to explain this distribution of voids based on what they call the sweepstake mechanism. And they were predicting that the distribution of the area of voids was having a power law with an exponent minus 5/3, which was independent of the Stokes number. So in 3D, the same kind of measurements were done again by Goto and Yoshimoto. And these times, basically, they do observe some kind of dependence on the Stokes number and some kind of things which are resembling the sweepstake mechanism extension to 3D, which was predicting that the PDF of volumes of voids was going like V to the minus 16/9. And so there were some recent experimental measurements in Grenoble, where they were measuring this distribution of voids, and indeed they do observe some kind of power law with an exponent which is close to 16/9. So 16/9 is 1.77777. So now I want to present another viewpoint, which is the viewpoint of turbophoresis. So what is turbophoresis? Is the fact, something which was used a lot in homogeneous flows, in flows where the level of turbulence depends on space, to explain that particles were willing to go out from the active turbulent regions and to concentrate in the place where the flow is more calm. And basically, so this you can see it as an extension to turbulent settings of what is known for thermophoresis. So thermophoresis is just that, imagine that you have a particle diffusing in a medium where you have a hot region and a cold region. So of course, in the cold region, the motion of the particle will be much slower, so that the particle will spend more time here, so will concentrate here, while here it will be faster and it will exit faster from there. So you expect to see higher concentrations in the cold regions. So this was used with success. So basically, since the 80s, to explain how particles are distributing in homogeneous flows. So for instance, in channel flows, or even in periodic flows with non-uniform forcing, so things like that. And typically, the idea is that one can get some kind of effective diffusion for the particles, which is proportional to the temperature, and which is nothing but the kinetic energy of the particle at a given position. Okay, so that's the idea. So the question I want to address is whether such considerations can extend to the case of statically homogeneous flow. And the motivation is the following: is that typically when you look at a simulation of a statistically homogeneous flow, if you look at the snapshot, of course, what you will see is something which is not homogeneous, where you will get regions, patches which are very active, and others which are much calmer. And so I will rely mainly on the use of direct numerical simulation and analysis from data of the direct numerical simulations. at these two Reynolds numbers here. And basically, the idea is to say that, of course, we will have some range which resemble what is known from a turbulence similarity from Komogorov 1941, but that the fluctuations there will play some important role for the particle distribution. So these are just qualitative ideas about what's happening. So what is shown here is a slice of the 3D turbulent flow, with the colored background here being the local energy dissipation. Okay, so high is yellow, blue is low, and as you see, that you have a very intermittent picture of the flow, where you can have places which are very close to each other, where the level of turbulence, which is measured by this local dissipation, can vary by order of magnitudes. And now, on the top of that, you have the black dots, which are the instantaneous position of these heavy particles. And what you see already by eye is that you have some anti-correlation between a high level of turbulence, like you have this yellow patch here, and the particle positions, which seems to be concentrated at the border of this patch. And this, so now what is shown here is just the upper top of this slice. So here is the coarse grain particle density. So here is the spot I was showing you, where you see that you have a void of particles. And what you see is that if you measure the particle acceleration at the same position, on the same scales, basically there is another correlation between high region of high acceleration and a region of low density. So basically this is what we see from a purely qualitative viewpoint. So now what I want to try to do is to model the particle dynamics, not to propose a model to do a large eddy simulation or something like that, but rather to suggest some observables and measurements to do on the particle positions. So what I'm just doing here is just stupidly rewriting, instead of saying that the particle acceleration is proportional to this velocity difference, we say that the velocity of the particle is the fluid velocity minus a correction, which is the acceleration of the particle itself. So I'm not saying that the acceleration of the particle is equal to the acceleration of the fluid, which will be the usual approximation of Maxey 1987. But what I'm saying now is that I want to coarse-grain this equation over a given time scale, so that I will say that the displacement of a particle over a time scale delta t is typically the time integral of this thing here, and the time integral of the other guy. Okay, so that's nothing magical. And then, so why is writing it this way? Is because now if I choose well my coarse graining time, this thing, which is a large scale quantity in turbulence, will have not changed much over the time between t and t plus delta t, while this thing, which is supposed to be a small scale thing in turbulence, will have fluctuated a lot. So maybe we can do something like applying some central limit theorem to know the fluctuations that we expect. So this, with this kind of argument, so we can write some kind of effective dynamics for the particles, where we have some drift, which is due to the large scale velocity and the mean acceleration over this time step, and some diffusion with a coefficient which is given by the covariance of the acceleration of the particles. So now the thing, yes, so what's behind this argument is to say that the time correlation of acceleration is very small. So this is something we agree to believe, because we know that acceleration is fluctuating over very small scales. But now the thing is that this quantity is actually having some non-trivial spatial correlations. So now what I've measured here is the correlation of the acceleration in space, but it's the flow acceleration, so for particles with zero Stokes number. And so there are some predictions saying that this correlation, according to some equations which are relating pressure and velocity fluctuations should scale like a power law with an exponent which is given by that, so something, and which is clearly less than 1. So having such an exponent less than 1 means that we have long-range correlations in the acceleration. So which means that if you were to measure from this power law correlation length of the acceleration, this correlation length will diverge, will be infinite. So now the thing is that our actual measurements are indeed, so which are the blue and red dots here, basically are showing that we have this indeed long-range correlations, but with a power which is less than 1, which is just the marginal case to have convergence, so which is a power which is of the order of 1, of -1. Okay, and so why is it important to take this into account? Because this is how the flow is organized, how it's correlated in spatials, in the spatial domain. So now the idea is the following: is to say, so if now I want to take into account these correlated fluctuations, so instead of just simply applying Kolmogorov 1941 ideas, I will make the flow fluctuate with something where I control how it's fluctuating as a function of scale. So this is what is called the refined self-similarity of Kolmogorov 1962. So where basically we say that everything in a given position is controlled by and at a given scale is controlled by how much dissipation we have in these specific regions that we are looking at. So basically we coarse grain our flow with boxes of a given size L. And so we look at what's happening inside this box in terms of local kinetic energy dissipation, this epsilon L, which fluctuates and which is known to fluctuate almost like with a log normal distribution. So this is very well known since the 60s, 80s. And this is also what is explaining why we have anomalous scaling in turbulence. Okay. So now that we have that, let's coarse grain the particle dynamics over this kind of box. So remember that what I want to average is the particle acceleration on this box. And what I will do is I will say that the local particle acceleration there, average over this box, will just depend on the local fluctuation of the energy dissipation coarse grain over this box. Okay, so I will estimate my variance of diffusion in terms of the local quantity here, conditioned on the fact that I have this level of energy dissipation. Okay, so now this conditioning will mean that locally, so I'm using this refined self-similarity hypothesis, all the particle statistics conditioned on this epsilon L will depend only on the local Reynolds number, which is defined through this local fluctuation of epsilon, on the local Stokes number, which is defined also by this local epsilon, and then when I need correlation times of acceleration or covariance of acceleration, I will just make dimensional analysis, rescaling them properly with the right epsilon in a turbulent manner, with a non-dimensional function of my two non-dimensional parameters. Okay, and then this will give some predictions on the statistics of acceleration and diffusion. So for instance, one thing that we can measure is some kind of bachelor scale. So you remember, this is how I approximate my particle dynamics, and then I want to see where do this term and this one are balancing each other. And this will be at a given scale, which is a kind of bachelor scale, below which diffusion will be dominant, and above which this part of the advection will be dominant. So now I measure this bachelor scale divided by L, okay, and show it as a function of scale for different Stokes number. And what you see is that in this range of Stokes number, so order unity or small, basically this ratio between diffusive and observation scale is remaining small. And in particular, it's decreasing with Stokes number and decreasing when I increase the scale. So further, so if I fix the Stokes number being with a particle response time of the order of the dissipative scales, and I go upscale in the inertial range, then my diffusive scale, my effective diffusive scale will become smaller and smaller compared to my scale of observation. So which means that I can neglect diffusion. Okay. So if I can neglect diffusion, it means that I can write an effective field, velocity field for the particles, which is free velocity minus the mean acceleration computed over my scale, my box of size L. And now what I can do is some kind of effective dynamics at such scale. So now I have a velocity field. I will just write the transport of density of particles with this velocity field. But the important point is that since my correction to the free velocity is something which has been built up when I was inside my box of size L, it's something is when my particle is exiting from my box of control, it has accumulated some history. Okay, so basically it's something where the particle is ejected from the box, and it's not just something as usual in diffusion process, which is appearing at the boundary or during a travel. It's something which is happening inside the box and make the particle go out. So which means that in the family of diffusive process, this will be an ejection process. Okay. So what does it mean? It means that if I write the effective equation for the coarse-grained particle density, what I have is I have the transport by the incompressible fluid velocity, and this will be equal to some kind of diffusion, where the diffusion coefficient, you see, is inside the Laplacian. So it's something which is not the usual diffusion. It's not conservative. It's creating mass. Okay? And this effective diffusion coefficient can be related to the local statistics of the particle acceleration. So now I can look again at balancing terms in these effective equations, and I can define a scale-dependent Peclet number, okay, which is basically the ratio between the diffusive time and the advection time appearing in this equation. And I can measure it for different Stokes number and different scales. So here it's various Stokes numbers decreasing this way as a function of scale. And here is the reverse. It's as a function of Stokes number, various scales which are increasing this way. And what you see is that in the limit of scale very large or Stokes very small, okay, so the Peclet number is increasing. Okay, so we are in the limit of very large Peclet number. Okay, which means that increasing means that diffusive time is much larger than the advective time. Okay, so diffusion is becoming more and more negligible. But of course, as you increase scale or increase Stokes number, deviation from the flow is smaller and smaller. So which means that, of course, this corrective term has to vanish. Okay? So now that we know that, so basically we can say the following is that now let's go back to our radial distribution function. So we want to measure. So we have some effective equation for density fluctuations. And what we would just say is that because of all the arguments I've shown you, I've tried to show you, basically this radial distribution function will just be independently of Stokes and length scale, will just be a function of this Peclet number, scale-dependent Peclet number. Okay? Scale-dependent Peclet number, which is defined, remember, like typically the typical velocity over a scale L divided by L times this diffusion coefficient. So now the thing is that, as you see, so the different data, they seems to try to collapse to the same master curve, which is the black line here. And for this black line, we have some prediction, which is a slope which is non-trivial, which depends on the statistics of the flow, at very small Peclet number, and another slope, which is -2 at larger Peclet number. And of course, you see deviations here because somehow, of course, it's finite simulation, so you have finite scales, and you deviate from inertial random statistics. But it seems reasonable and go from stocks of the order of 0.1 there to stocks of the order of 6 there. And so now the next point is that we can get other predictions from the model. So remember, it's an ejection process. So which means that we can imagine it this way. So we have boxes where each box is ejecting some matter. And now we can look at the probability of getting a void. So getting a void means that in this box, we will continue to eject for a long enough time without having matter entering from the other boxes. So that at the end, we can show that the probability to get a void somewhere here will be a power law. So somehow it will correspond to having a given rate, and then again a rate, and then again a rate, which will continue many times to eject things, so that at the end, the way we expect the probability to behave will be a power law at very small masses. So now concerning getting a large mass, I mean, this is more difficult, because what you need somehow now is not just to get the mass from the neighbors, but is to have your mass traveling from far away to finish in your box where you want the mass to be large. And this will be something which is actually super exponential. So it will be something like an exponential of a constant time the mass, and with again a log of mass appearing here. Okay, so something which is steeper than exponential and less steep than a stretch exponential. Not stretch, compressed exponential. So now, if we look at data, so this is data corresponding to a given scale and different Stokes number. And now, if you look at the tails, so we look at the same distribution, the cumulative distribution function in log-log. So we do see that we have this power law behavior at very small masses. And now, if you look at the right tail, so it's mass log of mass, semi-logarithmic, and then you see that you have straight things, which is like exponential minus something like mass log of mass. So the two tails are pretty well reproduced. So now the thing is that, again, with our arguments, we expect this distribution to depend only on the scale-dependent Peclet number. So here what is shown is different scales and different Stokes numbers, where basically all the one color will correspond to a given value of the local Peclet number, of the scale-dependent Peclet number. And what you see is that things are collapsing on the top of each other, there and there. Okay, so which means that indeed the inertial range mass distribution will depend only on this scale-dependent Peclet number. So just to finish my story, I'm going back to the connection with the distribution of voids. So what I told you is that the probability distribution of the coarse grain density is behaving like a power law, and then this power law should depend on my only parameter of my distribution, which is this scale-dependent Peclet number at very small values. And now, if I measure this exponent, so it's this exponent +1, which is shown here, as a function of this Peclet number, you see that indeed things are collapsing on a single curve. And this single curve is going to alpha equal to 0 for a finite value of the Peclet. Okay, and so alpha equal to 0 means that you have a finite probability to have an order 1 mass in a given point. Okay, so it's a divergence of the density somewhere. So we cannot go below actually this value. So now let's connect these two voids. So assume that we have indeed this power law, that it depends only on the local Peclet number. And we look at the probability to have a void with a sufficiently large size L cube, okay, larger than L cube. And this is the same as having our density less than 1 over L cube. So we have to have less than one particle in our box of size L cube. Okay? And this will behave like a power L to some power, and the power which itself depends on the scale through this Peclet number. So now we just make some approximation for what we observe for this power. So if we are below this critical Peclet number, it will be just V to the minus, volume to the minus 1. It corresponds to being on this side here. And if we are above this critical Peclet number, it will have this kind of form, with mu being the exponent that we observe here, this 0.4. Okay, so now we can look at the distribution of voids. So this is what we would measure if we were just looking at the CDF, cumulative probability distribution of voids, as a function of the void volume. So we say, oh, maybe there is a power, but maybe this power is depending on the Stokes number. Okay. But now, if we look at the same data but differently, so this time we rescale it in the proper way in order to cope with the behavior we had before, it seems that everything is collapsing on the top of a master curve, with one behavior which is -1, which corresponds to being on the left-hand side of this critical Peclet number, and then something which will approach another behavior which is controlled by this V to the mu log of mu. Okay, so just to summarize. So turbophoresis seems to act also in a statistically homogeneous flow, because this statistically homogeneous flow, they will have instantaneous non-uniformities. That there is an effective diffusion equation to describe the particle dynamics that will depend only on the local turbulent activity, and then that the way the particle distribution depend on both scale and particle response time can be encoded in a scale-dependent Peclet number, and for which we can get prediction on, for instance, the radial distribution function or the distribution of voids. Okay, thanks.
Thank you, Jeremie. We're open for discussion. Yes, please.
Hi, Prabhu here from Indian Institute of Science. Maybe I missed some aspect of your talk. In the very beginning, you said you are ignoring particle interactions, essentially assuming them to be point.
Yes, I'm ignoring. I'm considering the very dilute limits.
Dilute case, but then you're still getting the pair distribution function.
Yeah, but it will be, so if you want, it will be pair distribution function at scales which are much larger than the particle size.
Right. So then the pair distribution function comes from the fact that the particles affect the fluid flow, which affect other particles. Is that the case?
No, it's just the way the particles are reacting to the flow fluctuations. The particles are passive. So it's only they ignore each other, and just from that, I'm trying to get some prediction on how the flow is correlating their distribution over inertial range.
Okay, so it's purely one way. The fluid.
Yes, it's one way, and yes, it's only one way.
All right. So the second question is, right in the beginning, you said you were interested in predicting how the what do they call the bands around planets.
Yes.
Right. I mean, how does this have anything to do with the?
How can this have an influence?
Yeah, because I mean, my understanding is the atmosphere is so rarefied in most planets that have these rings, that does the analysis hold in that kind of scenario where the drag isn't, where the Navier-Stokes may not even be valid?
Of course. So for planet formation, there are a lot of questions. So one is whether the disk, the turbulent, I mean the disk around the star is turbulent or not, and how is the turbulence there? Is it some magnetohydrodynamic turbulence, or is it just pure shear, or is it some other kind of instability? Is it stratified or not? I mean, this is purely open. And the second thing is the second problem is that after some size, the dust particles are having collisions which are too violent. So it's called the meter size barrier by astrophysicists. Well, so particles which are more than a meter, when they have a collision, they tend to fragment each other. So that at the end you're not able to create larger things by just aggregation. So how this relates to that? I mean, it's just a drop in this ocean, of course. So the thing is that if you want to estimate collision rates, basically in turbulent settings, maybe compressibility will change something, maybe a magnetic field will change something, but here you need this radial distribution function in order to have some estimate on the collision rates. But that's all. Of course, it's a long way to explain everything.
Can you go up to the microphone, please?
A very naive question. So when you define effective temperature of particles in fluid, does it assume equilibrium distribution?
No. So basically, you define it through this diffusion coefficient.
Okay.
Which relates to the it's more related to the covariance of the acceleration, and not just to the kinetic energy. So it's not the pure equilibrium where you say that you have a KBT.
Yeah. Also, the preferential sampling of cold regions, you define, I mean, you use the kinetic energy of the particles. This is a very naive question. What if you use the kinetic energy of the fluid instead? Do you get the same result, that they preferentially sample the colder fluid regions?
Yes, it will, but it will describe the asymptotic of very small Stokes number, where you will still have this preferential sampling, but of course weaker than for larger Stokes numbers.
I have a bit of difficulty understanding one point, and I wanted to see if you could comment on it. So when you were developing the diffusion equation, you relied on the fact that the acceleration was very rapid in time.
Exactly.
But then it's correlated over very long length scales. How is that consistent with the fluid mechanics of the turbulence?
Actually, I cheated, of course. So the time correlation of acceleration can be very long depending on how you measure them. So if you measure, for instance, the time correlation of the modulus of acceleration, this will be very long range, correlated over the whole inertial range. But it's only if you look at components, because since components can vary a lot because things are turning, etc. So this looks like decorrelating. So I mean, this assumption has to be. I mean, there should be some components wise.
Does that mean?
But it's consistent in the sense that the long range correlation that you will observe as time is varying here will be anyway implemented through the spatial correlations.
Right, but so I thought these were taken as a dot product, which would mean that the vector nature comes in the long range part.
Mm-hmm.
It comes in the long range part,
Exactly,
but not in the short range? Is that the vector nature you're saying is, I'm confused.
So basically I should have shown another picture, which is, so if I measure, where is it? It's this thing. So if I measure this integral correlation time conditioned on how much dissipation I have, I measure something finite. Finite and not much larger than the time needed to go through my box of size L. Okay, and so then I say that maybe this applies, but of course, I mean, it's not. There is nothing exact.
So I just wonder, could this be accounted for? So in the end, you took the diffusion out, right? But could you account for it in a colored noise approach?
Yes, but at the end, I'm not using that as a model. Okay, I'm just using that to say, okay, this will be the important measurements that I want to do. I'm grabbing out the Speckley number out of that, etc. So certainly, the way one can get these arguments, it doesn't depend much on the fact that it's white noise. It's just, it's some kind of refined.
Well, since you don't choose that model, but I'm wondering if you chose that model and then took it as a colored noise, whether you could get the same result in a limit as you do.
So for instance, results like the functional shape of the distribution of particles, this is independent of the kind of noise I'm using. It's just depending on the fact that it's an ejection process. Okay. Then the fact that I'm introducing some Beckley number, which is scale dependent and Stokes dependent. I mean, at the end, you can see that as some kind of dimensional analysis, taking into account the refined self-similarity hypothesis of Kolmogorov. So that basically you make things fluctuate through the local. So it's, I mean, there is nothing very deep in trying to derive that, but this. The next step would be to use that in order to maybe do write some model, some kind of a large eddy simulation model for the particle dynamics. But I mean, I'm still far from that.
Other questions? Sure.
Sorry, I'm still trying to understand this. So, is this somewhat equivalent to having particles outside vortices, at the edge of the vortices? Although you have no vortices in your description. What the observation is that.
So if you look at this picture, okay,
right?
These are the vortex, okay. I mean, you see some kind of structure, you see some kind of tubes. These are the vortex. But what I'm doing is that I'm coarse graining on much larger scale. And I'm more interested in the fact that you have places with a lot of vortices and places which are almost empty, and how this kind of physical arrangement is fluctuating as a function of the Reynolds number, as a function of scale. Okay, so somehow, if you want, in my diffusion of the particles at small scales, it's taking into account the fact that things are ejected from eddies, and in a place where you have more eddies, you have more ejection,
right.
So you have more diffusion. Right. Okay. In a place where you have less eddies, there, of course, you have less excitation, right. And you are more likely to follow the flow.
Okay. All right. Thanks.
Okay, last call. Thanks so much, Jeremie, for this interesting talk.